All right, thanks a lot. So first of all, thanks to Zvi and Zhangbo for both having me give this talk, but also for allowing me to help organize this meeting. I think it's been a wonderful occasion. I was sorry to have to miss the first day due to some flight issues. So today I'm happy to talk about effective field theories of QCD. And let me just start off by a slide that's sort of related to what people have said many times, but I'll say it in my own way. And that is that QCD, in some sense, is the richest known quantum field theory that we have. Okay? It has the richest number of phenomena, and I'll just give you on this slide some indication of that. So it's really responsible for a plethora of what I call interesting states of matter, interesting phenomena, as well as interesting fields of physics. So we've all seen, let me push the right button here. We've all seen examples of hadrons, nuclei, neutron stars, quark gluon plasma. These topics have come up in other talks, as well as jets. So these are examples where QCD has some emergent phenomena, and those emergent phenomena are interesting, and we want to study them. With the advent of the LHC, we went even a step further and started exploring inside jets to so-called jet substructure. So it's not a stagnant field. The field goes on, and we actually start seeing new things and even new states of matter. What kind of phenomena are we talking about? Well, of course, asymptotic freedom. That's what we're here to celebrate. Confinement, which we've also talked quite a bit about. Chiral symmetry breaking. The QCD phases and phase transitions, very interesting. High temperature and density. How do things look? Deconfinement, et cetera. QCD is not just a relativistic quantum field theory where we have protons and neutrons that are bags of relativistic particles. There's also, you can think about heavy quarks. When you think about a heavy quark like BB bar, CC bar, so-called quarkonia, then you have non-relativistic particles, the heavy quarks, coupled to relativistic particles, and so you have confinement in a non-relativistic coupled to relativistic context. There's these exotics that have been recently discovered. So this is another example of something new. I put large NC down here on the bottom of my slide because I didn't know exactly where to fit it in, but of course it's been a very powerful technique. And in terms of what kind of fields or what kind of areas this field has led to, QCD, so of course there's collider physics, how we think about probing the short distance structure of nature, and QCD plays a crucial role in that. Factorization and resummation. So this is key to understanding the separation of scales in problems, as well as understanding how to make precision predictions. Gluon saturation, which you'll hear more about from Raju. Multi-loop quantum field theory. So QCD with strong coupling means that perturbative corrections are really important, and we actually want to go not just to the leading order, next leading order. Sometimes we want to go to next, the next leading order to really make precision predictions. And this involves sort of some of the highest precision calculations in quantum field theory with multi-loop amplitudes and multi-loop cross-sections. Flavor physics, so studying the electroweak part of the standard model, transitions between flavors of quarks, looking for CP violation. QCD plays an enormous role in that field because QCD corrections are crucial to understanding CP violating observables. Lattice QCD, which you heard about from Aida's talk, and you heard about earlier in the meeting for various talks, actually. Crucial method for actually calculating non-perturbative quantities in QCD. Not every possible non-perturbative quantity, real-time observables are a little bit tricky, but any Euclidean quantity, which really opens up a plethora of calculations that allows us to make sense of QCD. And finally, let me just say models, because we had a nice talk yesterday. And this is an example where you could think back to the bag model or quark models, but also we're thinking here of modern definition of models where we think about them as a way of exploring some of these QCD phenomena using toy quantum field theories that are maybe simpler than the full QCD in 3+1 dimensions. Okay, so each of these things on the right-hand side of my slide actually is a field. It's a field of physics where there are hundreds of researchers, they get together, yearly, and they talk about each of these topics. So this is not a small area of physics, it's an enormous area of physics, and Probably if you look at the archive, the most papers are related to QCD. Okay, let me say something about effective field theory. That's the subject of QCD that I'll talk about. So what's the idea of effective field theory? So we have a small expansion parameter, epsilon, and we want to think about the field theory organized as an expansion in this epsilon. The idea is really to take some phenomena, one of the phenomena on the previous page, and try to find the simplest possible field theory framework for describing that physics. And that involves identifying kind of what are the small quantities that I can expand in. So you really want to focus in an effective field theory on the infrared dynamics and try to simplify the treatment of the ultraviolet physics. Now, of course, we're stubborn and we don't want to give up anything. So we really want to carry out this organization in a way that we can arbitrarily correct it and include the physics of the ultraviolet in the effective theory. We don't want to give up any precision. We want to be able to really correct things to higher and higher orders. The key idea that makes this possible, of course, goes back to Wilson, and that is the idea of decoupling. So the physics of an infrared system, just shown on my chart here by some soft modes at some mass scale m, doesn't need to know about the physics of the ultraviolet. In particular, it doesn't need to know about the details of the dynamics of what's going on in the ultraviolet, shown here by these hard modes, which could be some heavy particles or it could be some far off shell fluctuations. Those types of things are not going to affect the dynamics of the soft modes, and so we can, we say, integrate them out and code them in the effective theory in short distance Wilson coefficients and make an expansion in m much less than this scale of the hard physics lambda. So how do we do that? So we do that by kind of 3 steps. One is determining the right degrees of freedom for the problem we want to study. That tells us what kind of quantum fields we're going to use to construct our effective field theory. What are the symmetries of the problem? Is there gauge symmetry? Are there global symmetries? And that's going to tell us how to construct the interactions. What's the expansion? How, and I already emphasized, what are the parameters epsilon that we want to expand in? So that helps us. The reason we want to do this is because it helps us to simplify calculations. It makes the approximation, more importantly maybe, it makes the approximations explicit, so you can't hide. And in particular, that also means that you are able to make estimates for the uncertainties. You know, if you're expanding in epsilon, you know what the next term roughly is going to be, so you can make you can tell people my uncertainty is 20% or my uncertainty is 5%. And that's kind of crucial when you're doing precision physics. So the modern attitude, of course, is that every quantum field theory is an effective field theory. Late in his life, and maybe earlier, but I found this quote in a lecture that Weinberg gave late in his life. He said, "This is a new and cooler view of quantum field theory," and I tend to agree. So at MIT, I teach an effective field theory course. I put a little self-promotion at the bottom there. It's a free online course. If your students want to learn about effective field theory, then they could show them this link. Okay, so let me talk a little bit about some of the concepts of effective field theory. So one of them is that we change the way we think about renormalization. This is sort of the modern view of renormalization. We don't have to have renormalization in each of these Lagrangians on its own, but there could be connections between them, and that's perfectly okay. There's the concept of making field redefinitions. We don't have to stick with the fields we are. Maybe we like some other set of fields better, as long as we have the same single particle states and we retain the same symmetries when we make field redefinitions, then we can do that. There's this notion of top-down and bottom-up effective field theory. I'll say a little bit more about that. There's a notion of matching and decoupling. This is the concept by which we take effective field theories, construct them, and build in short-distance physics, for example, into our effective field theory systematically. There's power counting in the effective theory, and in the simplest effective field theories, that's just the dimension of operators. But that's not always the case, and in actually some of the more interesting and subtle examples, it's not the case, and we'll say a little bit about that. Finally, there's renormalization group evolution, large logarithms, and universality. And I decided that what I want to do is start my talk off by talking about these concepts, but doing it in a way where I not talk about so much what effective field theory can bring to QCD, but quite the opposite. Historically, what did QCD bring to the field of effective field theory? Because the advent of QCD and the understanding of QCD was actually really crucial for formulating some of the concepts of effective field theory and pushing it to the level that we have now. So that's how I'll start. Then I'll come back and then I'll give some examples and it'll be the other way around, but we'll start this way. So let's start with field redefinitions. This really goes down to the idea that you can use your leading order Lagrangian, this L0. You can calculate the equations of motion from that Lagrangian. You can use those equations of motion to simplify the higher order terms. And the reason that you could do that is because you can make field redefinitions. This was understood early on. I think it was actually understood even in the early analysis of deep and elastic scattering that we've talked about. But it was really kind of made systematic in a couple of papers, one by Howard Georgi on what's called on-shell effective field theory, and then also a paper I quite like by Arzt, who really kind of systematized showing how it works when you make the field redefinitions in your path integral and taking care of all the various things that change, measures, currents, etc. And it's only true for S matrix elements, so that means we really have to think about when we compare theories, observables, physical observables, not green functions, just as one example. There's this notion of top-down and bottom-up effective field theory, and these things are kind of, I think QCD was really at the heart of making these things solid. Of course, bottom-up effective field theory, or the origins of effective field theory, and back in chiral perturbation theory with Weinberg in the 60s, where what a bottom-up effective field theory is means that we don't imagine that we know the upper theory, but we have the bottom, we have an understanding of the symmetry breaking pattern, and we can construct the most general theory, which I call in my slide here theory 2, based on the symmetries of the problem and the symmetry breaking pattern, without really needing to know the full theory. And that was the situation back in the 60s when we didn't know about QCD. In kind of another way, the top-down approach, we have theory 1, maybe that's QCD, and we want to take theory 1 and we want to remove some things. For example, maybe we want to remove the W, top, bottom, and charm because they're heavier than the physics we want to study at low energies, and we systematically integrate out and we do matching calculations to connect theory 1 and theory 2. So I think these concepts of bottom-up and top-down really owe a lot to the QCD. Then there's the actually carrying out the calculations to connect theories. And though the origins here are actually in guts, people were thinking about carrying out calculations in guts and going to higher orders and looking at unification. And when they were doing that, the calculations just got hard. They were doing that with an off-shell momentum subtraction scheme, which if anybody's ever calculated in such a scheme, it's not so easy. Of course, off-shell amplitudes are much harder than on-shell. And it really led to the kind of renaissance of thinking about using the MS bar scheme. And that, of course, is not a physical renormalization scheme. It means that you have to put the decoupling in by hand rather than allowing it to come out of the results. But that's okay, and understanding why that was okay, really pushing it to higher orders and understanding exactly where there are thresholds, et cetera, I think QCD played a key role in that. I mentioned this power counting. So if you want to prove that power counting is related to operator dimensions, you can do that. And you can just rescale your coordinates in some correlation function and think about the coordinates all scaling into some limit and enumerate your operators based on the dimensionality, do a little dimensional analysis. That really relies on Lorentz invariance because all your coordinates are being scaled in the same way. And many interesting examples in QCD are not Lorentz invariant. The physics is sort of not Lorentz invariant. There's sort of something happening and it's sort of setting up a preferred frame for some of the particles. One example of that is just heavy quarks. If we have heavy quarks, then there's they become non-relativistic, and the Lorentz invariance is sort of expressed as an expansion rather than just being manifest. Another example is hard collisions. Imagine we take proton-proton and we collide them, and then we maybe produce some jets or some Higgs particle. What's colliding is some particles inside the protons, say some gluons. But these are confined objects, and each of them is a very simple object in its rest frame, but in the collision, they're in two different frames. Okay? Neither one of them is in their rest frame. If I go to the rest frame of this one's even more angelic. The physics is kind of breaking the Lorentz symmetry because there's an axis, so the collider axis. The particles are coming in, and in each of their individual frames, they're kind of soft protons with lambda QCD gluons and quarks, but we have this frame breaking. And then the physics of the hard interaction actually forces us to think about the problem in these two different frames. So when you think about effective field theory for hard collisions, which I'll talk a little bit about later, it naturally also doesn't follow the dimension analysis type power counting. Renormalization group. Okay, renormalization group, the running of the strong coupling, the famous calculation of the beta function, of course, is manifest throughout QCD, right? Asymptotic freedom. And it depends on, for example, the number of light flavors. So the idea of making changes in the coupling from one flavor to another is kind of there from the beginning. And this notion in kind of QCD is absolutely crucial. If we think about a more general context of some effective Lagrangian as a sum of Wilson coefficients that depend on some high scales lambda and operators that depend on some low scales m, then knowing how the physics is organizing itself, really the renormalization group plays an important role. And so the way that that comes in this formula is this parameter mu here, and the couplings, which you may calculate at some high scale lambda in perturbation theory, you have to do some renormalization group and some logarithms, and that can change the values of the couplings quite dramatically. So when you are making predictions for low energy physics, the right coupling constants are different from what they were at the high scale. Okay, so it's crucial, for example, for the electroweak Hamiltonian, and it's really summing up logs of between the high scale and the low scale, and in QCD, sometimes these are even double logs. Finally, universality of short and long distance, and this is in some sense how effective field theory makes things simpler. We kind of want to reduce, reuse, and recycle as much as possible. By the way, the timer didn't go on. Yeah, so we have both physics that is sort of universal in the Wilson coefficients. Maybe our Lagrangian has some Wilson coefficients, and the operator contributes to more than one process, so we can recycle those Wilson coefficients. We don't have to calculate them for each individual process. We calculate them once and for all, and then short distance physics is universal. Or maybe there's some long distance matrix elements that are universal. They're showing up in more than one process, and we can reuse them. So both of these concepts are how effective field theory helps us to make predictions. These things, I called them kind of constants, but they could also be functions. Indeed, the part-time distribution function is an example of exactly that type of long-distance matrix element that gets recycled and reused. I didn't actually add this originally to my list, but I thought of it later, and then I stuck it on the slide without trying to mess up all my overlays. Symmetry breaking is also something that maybe even is the most obvious example of where making it systematic, understanding how the corrections work when symmetries are broken, and even making emergent symmetries manifest is something that effective field theory is good at. Okay, so that's kind of my picture of how QCD has really influenced the design of effective field theories. These concepts that are kind of key to every effective field theory, whether it's QCD, the standard model effective theory, condensed matter effective theories. Okay, those are non-relativistic typically and further from what I'm talking about today, but there's influence of QCD on the whole field of effective field theory, and it's a very general concept, of course. So here's QCD effective field theories in sort of a flow chart. So we have the mother theory in the middle, and then out of the mother comes all the daughters, okay, and sons. So, the origins were in chiral perturbation theory, effective theory of pions and kaons and eta in the SU3 case. But then the field is much more rich than that, right? So that in other limits like high temperature, there's hard thermal loop effective field theory, or high density effective field theory. I already mentioned energetic hadrons. The right effective field theory for that is called soft linear effective theory. So in these hard collisions, that's also the right effective field theory for talking about jets. Bound states of heavy quarks, CC bar and BB bar. There's non-relativistic QCD as an effective field theory of QCD. Single heavy quarks, bottom term, B meson, D meson, heavy quark effective theory. The top quark is an interesting example because the top quark is the one quark that decays before it has a chance to hadronize. And that still, the strong dynamics of the top quark is quite interesting, actually, because the top quark is a colored particle. How do we measure the mass of a colored particle that decays before it hadronizes? These type of questions depend on the QCD dynamics. And really understanding that requires kind of thinking about unstable particles and how do you encode that systematically in your calculations in QCD. coming the other direction. I started at chiral perturbation theory and then went this way, but I'm now going to go this way. Chiral perturbation theory, if we add nucleons, leads to another example of chiral perturbation theory, but if we add more nucleons, it gets even richer, and we can start to understand nuclear forces. Small x physics, which you'll hear about from Raju, is another example. Perturbative QCD and this decoupling of mass flavors was a further example that we already alluded to. And in Aida's talk in particular, you heard about lattice QCD effective field theories, controlling the parameters of lattice QCD, like the lattice spacing, the pion mass, the volume, and heavy quarks. So there's examples of lattice QCD effective field theories that I'm not going to touch on in my talk at all, but that sort of play in with the continuum effective field theories. So this picture also gives you an idea of how rich the field of QCD is.
What would be asterisks?
Yeah, so the asterisks stand for the fact that in these theories, there's really a playoff with the lattice QCD. It's really kind of being used, and it can be used in modern times in an extensive way to help understand these effective field theories, whether it's in chiral perturbation theory, carrying out matching calculations that have to be done non-perturbatively, or understanding the potential in non-relativistic QCD, or understanding certain matrix elements in heavy quark effective theory that are non-perturbative. So there's a tie between lattice QCD and these effective field theories. Thanks for asking. Okay, so now I just want to sort of turn things around, go the other direction, and talk about a few examples. I won't be able to talk about all the examples in this chart, so I just picked a few, and we'll go through them and talk about how effective field theories have been used and kind of where things stand. I'll try to get to some modern examples. So chiral perturbation theory, we'll start by rewinding and going back. Originally formulated here for pions with SU2 left cross SU2 right, breaking to the diagonal group SU2V and due to the chiral condensate. And of course, we also have explicit breaking due to the quark masses, and we understand how to construct the chiral Lagrangian for that. It's derivatively coupled, and that's related to the fact that there's a nonlinear realization of the symmetry to encode the fluctuations on the vacuum manifold, and we don't care about fluctuations that aren't space-time dependent. So we have here this exponential representation. And this is the leading order Lagrangian that one can write down, and you can do that from the bottom up, and that's what Weinberg did. The quark mass term, of course, is giving mass to the pions, so they're pseudo-Goldstone bosons rather than Goldstone bosons. There's important to figure out the power counting is to understand how the 4 pi's come in, and the power counting expansions here are actually momentum squared over the chiral symmetry breaking scale, lambda chi squared, where you can think about as 4 pi times the pi and decay constant f, or m pi squared over lambda chi squared, so these are quite good expansion parameters. And if people quickly went to higher orders, so Gassler and Leutweiler in particular should be called out for carrying out the analysis of the p to the 4 corrections and understanding how all that worked. And then, of course, this is very fruitful field because you can make predictions for multiple pion processes. And through parameter-free predictions, you fix these parameters in the leading order Lagrangian, you expand that exponential, and you can get multiple pions for free. And Weinberg did that for predicting the pi-pi scattering lengths, and it's been fruitful ever since. Of course, you can couple electromagnetic currents too, or weak currents, and that's also very fruitful. Things get a little more rich when you start thinking about adding sources. A nucleon is a source for the pion, and you can think about pion interactions in the context of nucleons. I didn't try to write out the Lagrangian, but I just mentioned here that the expansion gets actually much more delicate, in particular when you have these additional expansion due to the nucleon mass coming in, and people are still talking about how the right way of organizing this chiral perturbation theory, how it should be done, and it's related to sort of putting in the cutoff and carrying out and having a systematic expansion that converges nicely. Things get even more interesting when you have more than one nucleon. So if you have 2 nucleons, then you take what you had before, and now you add couplings of pions to 2 nucleons, but you also have short distance physics. You can think of this as sigma meson or rho, et cetera, higher mesons that you've integrated out. And they're creating contact interactions, the short distance potential for the nuclear force. And so you can think about those as some kind of four quark operators. They're the quarks here are fermions, which are the nucleons. And Weinberg realized this back in '90, and then it's been elaborated on by many authors since then. And I decided, since that's sort of the more, the later thing, to have a couple slides giving examples of sort of some modern results in this last category. So just thinking about the impact of two nucleon potentials, Applebaum and collaborators have carried out calculations up to N4LO. So at a certain point, you stop writing the N's out, because N, LO is too much for anyone to say. So we say N4LO. And so you start out with just contact interactions and pion exchange, short distance and long distance, but then you have to correct it. So more contact interactions, more pion exchange, and you go on. And things look quite nice here. You see the higher orders, which are the blue, purple, are converging towards what you can effectively think of as data. You can also think about coupling sources, electromagnetic source, for example. Yeah, so this is actually potential model fits the data, and the potential models are so precise that you can treat them like the data. Yeah, but you can really think of it as data. So coupling electromagnetic sources, also work by these authors here. And I give just one example, which is thinking about the deuteron, which is a bound state of neutron-proton, and thinking about its coupling to electromagnetism, in particular thinking about its quadrupole moment here, and sort of seeing how that evolves as you go to higher orders in the expansion, and you start to get something quite precise where the cutoff dependence is getting small. And maybe it's not as precise as you could get from doing spectroscopy, but this is a calculation. So the fact that you can fix all the parameters and make a prediction for this quantity is still quite, with this kind of accuracy, is impressive. Okay, so let me talk, I've already mentioned, but let me talk about QCD effects for the weak interactions. And this is, I think, an important thing to understand, that when we think about physics of flavor transitions, QCD plays an important role. And I'll just give one example, and that's beta S gamma. So this is a flavor-changing neutral current. You can't go directly from B to S at tree level. You have to go through a loop. And if you think about integrating out your W's, your Z's, your tops, and your Higgs, then this Feynman diagram here collapses down to a point and gives a bunch of operators. And it's not just this diagram. There's other diagrams, but you get a bunch of operators. One of them is this magnetic operator, chromomagnetic type term, or electric, coupling to the photon here, F mu nu, with a strange quark and a bottom quark. And you can think about looking for new physics by searching for whether the value of the coefficient, the Wilson coefficient, C7 of that operator, if you measure it experimentally, does it agree with the standard model? Because in the standard model, we can predict it, we can calculate it. If you calculate it at leading order, just from like this diagram, you get minus 0.2. But QCD plays a crucial role, because you're not doing physics at the mass scale of the W in the top, you're doing physics at the mass scale of the bottom quark in the beta S gamma decay. So you want to think about this coupling and evolve it down to the bottom quark scale. That actually involves some two-loop anomalous dimensions for reasons I don't want to get into. But it changes the branching ratio by a large amount, 50%. And the branching ratio, it changes the coefficient by 50%. The branching ratio is the coefficient squared, so it's more than a factor of 2. Coming from these leading log QCD running effects. And because of the size and importance of this, it became a whole program of physics in the flavor physics community. And you see, like a lot of authors here, they made a plan to do all the calculations needed to go to next and next leading order. And that involved calculations up to 4 loops for the anomalous dimension. So here's just one of the 10,000 diagrams that they had to compute. And so this became a precision science. And I'll just spend one example. I've worked in this field as well, and one thing that I've done together with some experimentalists in a collaboration known as the SIMBA collaboration is done fits for this Wilson coefficient C7 while simultaneously trying to control non-perturbative effects. In this case, there's a bottom quark parton distribution function that simultaneously you have to control along with thinking about the short distance physics I was talking about. And we've done global fits to the data, both trying to understand the uncertainties in that so-called shape function or bottom quark PDF, while simultaneously extracting the norm from the data. And there's perturbative QCD effects that come in here as well. And things agree with the standard model, unfortunately. but it's also a great success of the Standard Model that we have this level of agreement. And the size, the gray band here is the prediction of the Standard Model, and dominated by charm quark effects actually that are missing in the calculation so far. Okay, let me talk about a different effective field theory, heavy quark effective field theory. So I already mentioned the physics of a bottom quark, and we think about the physics of a B meson as a bottom quark surrounded by brown muck, a term I think that Georgia coined, where light quarks and gluons are building up the state. And they're described by just QCD, but the heavy quarks here, we can integrate out the mass scale and think of it as a static source. It just sort of sits at the center of the B meson and provides a color source for the light stuff. And when we do that systematically for both bottom and charm, we lose dependence on the bottom and the charm mass, and we lose dependence on the spin. So we have a U4 heavy quark spin flavor symmetry, and we have this effect of Lagrangian here, which you can think of as having a 4-component spinner, and there's a U4 symmetry for that 4-component spinner, which includes both flavor and up and down. How do you do phenomenology? Well, there's various examples. One is the semi-leptonic decays, where there's famously a single form factor in this limit, and called the Isger-Wise function. There's symmetry breaking from 1 over m corrections, and even that, there's no corrections at 0 recoil. And this led to, on the lattice, a dedicated program of calculating the form factors, building in the knowledge from the flavor symmetry and heavy quark flavor spin symmetry, and really getting precision results for VCB by comparing to data and knowing these form factors. This also gives me an example where I can illustrate the aspect of universal nature of effective field theory that I mentioned. In particular, when you look at the 1 over m corrections in HQET, there's kind of two different operators, kinetic energy term and the chromomagnetic term. So kinetic energy term dt squared here, chromomagnetic term sigma coupling to g. The chromomagnetic term breaks the spin symmetry. The kinetic term doesn't. It just breaks the flavor symmetry from the 1 over m. And these same matrix elements show up not only in, for example, hadron masses, but also in inclusive operator product expansion for the inclusive process of a B going into a charm quark. And that's actually a very nice OPE because at leading order it's completely perturbative, and then the corrections are coming in at 1 over m squared, actually. Now, I decided not to talk about the OPE, I just talk about hadron masses. So this term here is what causes a mass splitting between the B star and the B. B star and B are related by heavy quark symmetry, and the D star and D likewise are related by heavy quark symmetry. This thing is has no flavor. And so if you take this ratio shown here, MB squared star squared, I'm not going to read it out, and you divide by the analog in the D system, this is completely short distance. The non-perturbative parameter, which is the same in the bottom and the charm, cancels out. So we get a ratio of Wilson coefficients that can calculate these ratios of mass splittings. And then there's some corrections at higher order from 1 over m effects. And people, in particular Grozen, calculated these Wilson coefficients up to 3 loops. So this is very nice. And I'm showing over here what it looks like. At leading order, it's 1. And if you do it in the MS bar scheme, at next leading order, you get this dashed green. And that looks very good because the data is actually, depending on whether you're doing up or down or strange mesons, is the dashed lines here. So you're pretty close at next leading order. At next to next leading order, you get actually a further away. So you're down here. And Grozen's calculation takes you down here. And you're so, such a beautiful result. What's going on? So it turns out that, we all love calculating an MS bar, but there are some subtleties, and in particular what are known as renormalons. And this is an example of where MS bar is not properly separated the short distance and long distance physics, and you have to be more careful. And if you're more careful by using some schemes other than MS bar, you can remove renormalons, and you can remove this poor behavior of the perturbation series that you're seeing here. That's given by, in this chart, the solid curves. And then things converge nicely. Your higher order calculation converges to something. This parameter here that I'm showing is some scheme parameter related to the definition of that scheme that removes the renormalon. And you can see sort of maybe for keeping this in some kind of perturbative regime that you're getting something that's pretty close to the data. So again, now it becomes a success story, but you have to, sometimes QCD is subtle and you have to be careful. Yeah, R0 is like a cutoff. It's like mu. except it's a cutoff here for linear divergences. So I called it an R0 instead of mu for that reason. You don't have to take it exactly equal to the cutoff for logarithmic singularities. You could, but that's why I gave it a different name. Okay, so finally, let me turn to the final example, which is soft linear effective theory, a theory dear to my own heart. And it's a theory that we continue to explore and continue to kind of come up with new examples and new applications for. It's also a very rich effective field theory. You know, back in 2000, I had no idea that it was going to be as rich as it's become. So it can be used for a lot of different examples, in particular examples that are related to collider physics, which we're very interested about. I already mentioned jet substructure. There's SET examples for doing that. B decays are something that it can be applied to. It can be combined with NRQCD to do Quarkonia. And it enables calculations of resummation at higher orders than people were able to do before. Study the structure of infrared structure of gauge theories in novel situations that are more complicated than you might otherwise want to treat, more scales in the problem. Effective field theory tells you how to organize them. Subtractions, Keith already mentioned this in his talk yesterday, but understanding factorization for subtractions, in particular this example of N-geniness, is something that was done with SET. You can do subleading order. So we all understand what QCD looks like in collinear limits and soft limits at leading order, but what does it look like at subleading order? What's going on? This is something where you can use the effective theory to explore. Okay, so how does it kind of work? So factorization, if we think about factorization of perturbative and non-perturbative physics, looks something like this, where there's some short distance perturbative cross-section tied, for example, to parton distribution functions in a proton-proton collision. And maybe there's some non-perturbative physics in the final state as well. For example, maybe we have a hadron that we pick out of a jet, and we have a fragmentation function for that hadron. So there's universal physics here, fragmentation functions and parton distribution functions. There's also universal physics in the perturbative part of the problem, because often the perturbative part of the problem involves multiple scales, and then there's logarithms between these scales, and we have to do resummation in order to have control over the precision level that we want for the cross-section. And so SET basically organizes things. It organizes the scales, and it tells you how to resum logarithms. So in this picture here, I have kind of a hard function. That's the short distance collision. There's the evolution of the collinear objects, which I had this green initial state object and these blue final state objects. And so it organizes the physics of the collinear splitting and virtual effects, which are universal from the hard collision. Then organizes the soft physics, which is iconal typically, and gives some universal functions. And allows you to sum logs. And these logs are typically in the collider physics, they're double logs, so the Sudakov double logs. But we don't want to just have the Sudakov double log with e to the minus alpha log squared. We want to go to higher orders. And in particular, people nowadays are kind of generically talking about next to next to next to leading log, and even have done N4LL now. So very high orders. The way that it works is we have effective theories for different regions of momentum space in the kind of the way I described to you earlier. And we integrate out systematically. So we go down this chart on the right and we remove scales one at a time. We remove the first scale, which is the hard scale. We get some short distance Wilson coefficients. We calculate them and organize the operators. The operators are built out of quarks and gluons. But because of the color dynamics and the way that things work because of gauge symmetry, there's actually Wilson lines that immediately pop up and attach to your quarks and gluons to make kind of, to parallel transport them and connect them from different regions of momentum space. So in this picture here, we have, for example, maybe we took two green gluons from the initial state protons, so we have these B objects, which are adjoint Wilson lines attached to a G mu nu. And then in the final state, maybe we have a QQ bar initiating two of the jets and a gluon initiating the third. And then we would have an operator that's got this structure here, built out of building blocks that are Wilson lines attached to quarks, but they have directions associated to them. That's the breaking of the Lorentz symmetry that I was talking about. Each of these collinear directions is its own field theory. And if you just looked at it all by itself, it would look like QCD. You know, QCD for the initial proton here, QCD for the initial jet there. But then the effective theory tells you how to couple these versions of QCD together and how they talk to each other, which is through the hard interaction or through soft dynamics. So the way the Lagrangian organizes itself is sort of hard scattering that's coupling those versions of QCD together, dynamical Lagrangians, which are avoiding double counting but having kind of copies of QCD for the different things in the infrared that one is describing. And there's something known as Glauber exchange, which is a long distance effect that can also couple things together. I won't say very much about it, but proving factorization is actually proving that this thing doesn't matter. And this physics factorizes because basically your dynamic Lagrangians are independent. You have independent dynamics for the jet from the initial state, and your hard scattering is just products of operators in these different sectors of the theory. And so you have a product at a hard scattering operator. It only shows up once, as George was emphasizing. Your Lagrangians factorize into a direct sum. That means your Hilbert space factorizes into a product. So you can factorize things, and you get factorization formulas. So let me give you, in the remaining minutes, let me give you some examples of how SCT has been used, and I just picked 3 examples here. So one is in calculations of higher orders, and I'll give an example with E plus E minus to dijets. So we can calculate what's called thrust, T, as Eddie Fari initially invented. What we like to talk about is 1 minus thrust, so I call that tau. As tau goes to 0, that's the dijet limit. And we have a factorization theorem that describes that in terms of a hard coefficient function, which is just a form factor, or normalized version of a form factor, a jet function. Well, there's actually 2 jet functions here, but thrust makes a symmetric rejection, a soft function, and even some non-perturbative soft dynamics, which is the leading non-perturbative soft dynamics. So we can describe all of this by factorization theorem. And this factorization theorem is only describing the sort of limit as tau gets small, and then there's some corrections that are coming from power corrections in tau. And you can see in this chart here how big those corrections are. So the solid line, blue line, is the singular, meaning the terms that you would predict with this factorization theorem, actually at 3-loop order. And the non-singular is the dashed line, which is smaller, but you can include it as well. And then you get the total, which is the black line here. This is a magnitude of cross-section, so some of them are negative. Somehow my axis label disappeared. So this was something that we used in order to make predictions for the strong coupling constant, meaning fitting the strong coupling constant to LEP data. And this program started with a nice paper by Becker and Schwartz and using SCT to go from what were previously next to leading log calculations, and they jumped 2 orders. They did next to next leading log, and at the same time next to next leading log. And that was just showing the power of thinking about this problem from the effective field theory point of view. We added in just treatment of the power corrections and some other things, including renormalons and other small effects, and did a global fit to the data. And just to give you a feeling of how it works, I'm showing here some cross-section plots. If you just calculate thrust in fixed order, you're getting more and more precise predictions, but the overlap doesn't look great. It's kind of like Keith mentioned as well. Sometimes when you're making uncertainty estimates, they work less well. If you do the resummation, then things start to look good in the sense that your uncertainties are now overlapping. Things seem to be converging as you go to the higher orders. If you include the non-perturbative effects, then they have the effect of shifting the cross-section. And so they go from that picture to this one. And if you remove the renormalons, then you get even more precise results because there's some large corrections that are sort of trading off between your perturbative and non-perturbative problem, again in the MS bar scheme, so you can switch to a scheme that's more accurate and get a curve that looks like this. You fit to the data, you're doing a 2-parameter fit of alpha S and the power correction parameter, and it looks beautiful. It's not just fit to the data that's shown on the screen, but to data at various different Qs, low energy experiments, LEP also at 200 GeV, not just at the Z-pole. And your chi-squared is 0.9 per degree of freedom, so you're happy. Until you look sort of at the value of alpha S that you get out, and you're like, why is it so small? So this is showing going from lower orders to higher orders, and things are sort of contained, but the value of alpha S sort of creeps down, and once you get to the highest order, into this low value. And this has been a puzzle for over 10 years as to why this disagrees so much with the world average. But the fit looks beautiful. And of course, when we were writing this paper, it took us 2 years to write it because we were so worried about what's going on with this small alpha. And that was partly why we, calculated the QED effects. Maybe it's something with the Q. No. B quark mass effects. Maybe that'll do. No. Okay. So we kept trying, but it remained small, and then we published. You can do some cross checks on that. You can use, for example, the first moment of the cross section rather than a fit to the spectrum. That's useful because when you fit to the first moment of the thrust cross section, it actually doesn't really care about logs anymore. So you're no longer really, your highest order fixed order calculation is pretty much in agreement with the highest order resum calculation. So the logarithms are not playing a key role, but the same non-perturbative parameter is relevant, for example, if you fit to the first moment. And so we get this red curve from this red blob from the first moment, and it agrees quite well with if you look at the outer circle, which is the 1 sigma in 2 dimensions, with the earlier blue blob from the fit to the distributions. We've cross-checked it with other calculations like the C parameter and confirmed the universality of the power correction. Also gives a small alpha S. And recently with some of my students, I did a prediction for the energy-energy correlator using the results from the thrust fit and found agreement with the data in Opal, again from LEP, without any free parameters. So these are kind of cross-checks. There's still some puzzles here, and maybe it has to do with 3-jet power corrections, and there's some recent work in that direction. But I think it's something that we still need to sort out. Okay, so 2 more quick examples in my final time. One is going back to an LHC, and we talked about the gluon fusion. SET has been used, for example, to treat fiducial cuts. So when we think about these measurements, they're not just fully inclusive. There's always cuts that experimentalists have to make. In particular, maybe they demand that the photon energies are above some thresholds, and that's what they do. So these are Atlas cuts here. How do you build those into your calculation, and what effect do they have? Well, it might seem simple. You just have a prediction for some hadronic tensor, and you integrate it with the right phase space acceptance. But there's subtle effects that happen, and that's because these cuts can actually make resummation more important. And in particular, these types of cuts here, if you look at the photon transverse momentum, if there's 0 transverse momentum of the Higgs that's producing the 2 photons, then you would sort of, for 0 rapidity, they'd be back to back, and they'd each carry half of the Higgs mass away. And that would be 0.5 in this plot. And when you make cuts, you sort of make yourself more sensitive to the QT equals 0, and that's where the singularities are, okay? And so you're having resummation effects that are coming in to sort of cure the QT equals 0. There's a well-known resummation for small transverse momentum. This is so-called physics of transverse momentum parton distribution functions, et cetera. And you have to carry that out because the fiducial cuts are making it more important. When you carry that out, then you can get accurate predictions. So there's lots of results that go into that, which I've listed all on the slide here. The data, this is an example with Higgs where the theory is ahead of the data. Drelian is exactly the opposite, where data is well ahead of the theory. So we have a nice complementary between different observables. And let me close with one final example, which is subleading power, which I already alluded to. So soft linear effective theory allows you to go not just for the leading power, which are these logs here, which I've multiplied by tau, but it would be logs of tau divided by tau if I was just looking at the thrust cross-section, but also the next order. And the next order just suppressed by a power of tau. What is the factorization for that? How universal is it? Are there concepts like the cusp anomalous dimension here? How universal are the anomalous dimensions and the functions that show up? What kind of effects like Sudakov? How does Sudakov suppression, which is an exponential suppression at leading power, how does that work out at subleading power? Is there a new type of Sudakov? Can we improve fixed order calculations? It's related to what Keith talked about. And there's examples also in the effective theory where you just start at subleading power, for example, in B physics. So it's another reason to look at it. I'll just focus on one thing, which is this one I made red, which is Sudakov suppression at subleading power. The way that it works is we have kind of corrections that come from subleading hard scattering, where maybe our jet is formed by both a quark and a gluon rather than just a quark, as well as subleading Lagrangians that we have to insert to correct the dynamics. This is sort of generically how things work. And it gets complicated at subleading power, as you might imagine. Factorization theorems are no longer a single term, it's a sum of terms. And the sum of terms can have kind of interesting interplays between the terms. So there's an interesting example that happens when one of your quarks is not collinear and energetic, but becomes soft. That's a subleading effect. And there's kind of soft quark corrections as well as collinear quark corrections, and they have an interesting trade-off. And I'm not going to try to describe this kind of everything in this little figure, but it's kind of a picture of how the factorization works out. And there's a subtle effect that happens, and that is that there's what's called an endpoint singularity. And it means that the factorization theorem that we wrote down, we might have written it down as a bear, we're used to thinking of renormalizing the objects inside of it. And then we just tie things together with those outer integrals. And that just works. In this example at subleading power, it doesn't work. The integral that's tying things together diverges. And so it's more complicated to think about because you thought you factorized the physics into these different sectors, collinear, hard, soft, et cetera. But the tying together is causing new divergences. And this is something that people have known about for years. I mean, it goes back to when people are doing exclusive decays, Brodsky-Lepage, et cetera. People knew that at subleading orders in the expansion, you ran into these types of singularities. And here, we now actually know now how to deal with them in SET. We figured out how to deal with them. And the example that I'm showing on this slide is just showing that you can actually do resummation at subleading power. There's something called the soft quark Sudakov. It's got kind of a weird structure with CFs and CAs. We conjectured it in one paper, and later there's a Benecke and collaborators who actually proved this formula. And then in order to prove it, you actually had to understand how to deal with these endpoint singularities in a renormalization sense. And there's a refactorization that goes on where you're moving some parts of your factorization theorem from one place to the other. And I won't go into the details, which are rather complicated, but you can actually get results out once you understand that. And this is, I think, something that can be applied to a lot of different examples where these endpoint singularities show up. All right, so I'm done.
So we're a little over time, so we're going to have time for one question. So, oh wow, we have a lot of people. We only have time for one question, so who's got the best question? Over there. So wait till you get the microphone.
So in the days before QCD, people like Dalitz, Lipkin, developed what is now referred to as non-relativistic quark model.
Yeah.
And in retrospective, it works too well.
Yep.
Now, it seems like an ideal challenge for this sort of toolbox to understand why it works so well when it works and when do we expect it to fail.
Yeah.
And I would love to hear your thoughts about this.
Yeah, personally, it's not something that I've worked on, and I don't have too much to say, but like in this context of these models of QCD that people are studying, that Igor was talking about, this is an example where or doing light front, where you can make contact with some of those old ideas coming from a modern perspective and try to connect, I think, to constituent quarks and such things. But I don't have too much actually to say about it. Maybe that was such a short answer, we could take David's question.
I just want to understand what MSR, how you remove the
Yeah. So MSR, we called it MSR because it's related to MS-bar. It turns out you can use the same perturbative knowledge that you got from the MS-bar scheme to subtract the linear divergences, because the MS-bar scheme, basically in that perturbation theory, it has a linear divergence that's related to the renormalon, and you can set up a scheme that uses the same perturbative ingredients to subtract with a linear sort of correction, and that's what the MSR scheme is. You can think of it in your mind as a way of, why don't we do Wilsonian? It wouldn't have these problems. We don't do Wilsonian because it has other problems. Imposing gauge symmetry in a gauge theory like QCD is tough. Doing calculations is tough. You can think of this, but then MS-bar, is beautiful for calculations, but it has these issues. And you can think of this MSR as sort of a way of taking MS-bar and perturbing towards Wilsonian, because you're putting back the linear cutoff effects.
Okay, let's thank the speaker once again.